Hello and welcome to the fifth lesson in Unit 1, and we're talking about uniform and non-uniform motion. So the goal today, I want you to be able to explain the concept of uniform and non-uniform. So basically what uniform means is that we have the cruise control on. All right, we're traveling at the same velocity all the time, so we have cruise control on. Non-uniform is accelerator down, all right, or let's just say gas down. Giver. Okay, so that's your two differences here. Uniform, you got cruise control on, window down, relaxing. Non-uniform, you're trying to impress someone, you got her right down to the boards and you're giving her. All right, there's the difference between the two. So I want to take a look at two graphs here. So again, we're creating distance time graphs. That's what I have here, displacement time graphs. So displacement, going to be in meters. Oops. Except this time, sorry, it's a velocity time graph. So it's actually velocity. All right, on there versus time. All right, so I'm sitting in the car with you and I'm recording the velocity at these given times. All right, so I'm looking over your shoulder, I'm looking at the speedometer to see how fast you're going. All right, and time. And then we're going to make a graph with it. So the first example here, your car, you're speeding up, and this is the information I collected. So again, everything across the bottom here, let's actually cross out, if you scratch out the 10 and the 20, we'll just go up by ones here, make it easy to graph. Okay, so the first one, plotting my points, 0, 0. After 1 second, we're at 5. So it goes up by 2s, 2, 4, so it's going to be in the middle. 2 seconds, we're at 10. 3 seconds, we're at 15, so in the middle again. 4 seconds, we're at 20. So this is what happens when you are got the pedal down, you're accelerating, drawing a line here. Again, it's a linear relationship, okay? Which means if we have a linear relationship, we can calculate, picking easy points here, we can calculate a slope. All right. Okay, so we can find the slope. I'm going to talk about in the next slide what that gives us. Okay, so velocity, I've plotted them. So this is what we say is our acceleration. This is accelerating. All right, put the gas pedal down, and this is what it's going to look like in your average car. Now, once you reach top speed, 20 meters per second, I tell you, okay, now hit the brakes. All right, this is us decelerating. Okay, so when we plot this one, 0, 20, it starts up here, 114. So again, how about we just cross out the 10 and 20 off the bottom just to make our lives a lot easier. Okay, so 14, 2, 4, 6, 8, 12, 14, 2 and 8, 2, 4, 6, 8, 3 and 2. Now 4 and negative 4, where does that fall in our graph? Technically, that goes below the graph here. What does that mean? When you have a negative velocity, right here, you're backing up. So you really wanted to stop. You threw your car into reverse and started in reverse. Not recommended on transmissions unless it's your best friend's car, then you can do that. But for the most part, we're going to stop at 0 if you put the brakes on. And this is what a lot of pure physics teachers will cringe at this, but this is what we call decelerating. It's not a preferred word. They prefer you use accelerating all the time. But I mean, for us, let's keep it simple. It's accelerating, decelerating. What's the difference between the two lines here? This one we have a positive slope. All right, the line's going up and to the right. It's a positive slope, so we assume, or we call that acceleration. Here we have a negative slope. All right, it's going down to the right, so we call that decelerating, or deceleration. All right, so there is your two different types of velocity time graphs that we're looking at. What I want to do is I want to look at the math, the slope on this other slide. So I said already, the slope is kind of what we're interested in here. So let's pick some easy points here, and then we'll go right to the end. So here is our right angle triangle, so we can find our slope. So I want to keep the math a little bit separate here. Slope is rise over run. So we are calculating acceleration, and now I want to show where it comes from. So each square is worth 2, 4, 6, 8, 10, 12. So 14, and on the bottom 2, 4, 6, 8. Now remember, across the bottom of our graph, we had time in seconds, and up here we had velocity, which is meters per second. So that means that our slope is going to be our change in velocity, and velocity divided by change in time. All right. So what does that give us? Well, we know the change in velocity was 14 meters per second. So we changed our velocity 14 meters per second. So we started at 6 meters per second. We ended at 20. So we increased our velocity by 14, and we did this in 8 seconds. So there's your definition of acceleration. How much you change your velocity in a given time frame. And acceleration is just a small a. You don't have to write it out every time. So 14 divided by 8, that's whatever, 7 divided by 4. So we'll just leave it as a fraction. I'm not too worried about that. Now here's where the units, and you don't have to ever do this again. I just want to show you meters divided by seconds, divided by seconds. Rules of fractions. We never divide. We take the bottom one, and we multiply by the reciprocal. Meters times 1 is meters. Seconds times seconds is seconds squared. So that is why acceleration is always a distance divided by a time squared. So meters per second squared. All right. So that's how you calculate your acceleration. The change in velocity divided by change in time. Okay. And it's always in distance, so it'd be kilometers per hour squared. For the most time for us, it's going to be meters per second squared. All right. So our examples. Motorcycle from rest. Now from rest means he's starting at 0. All right. Starts at 0 meters per second. And he undergoes constant acceleration. So this is non-uniform. Okay. Holds the throttle down and reaches a velocity of 21 meters per second. So that's his final velocity. And there's our time. So what is the average acceleration? Well, acceleration is your change in velocity divided by time. Change in velocity. Remember, I'm going to say remember, but change in velocity, if you're not familiar with that notation, it is your final velocity minus your initial or start velocity, or some people might be comfortable with V2 minus V1. Okay, so if I was to list the information, my first velocity was 0 meters per second. My second velocity was 21 meters per second, and my time is 8 seconds. So if I list it off to the side, then I have 21 take away 0 divided by 8. 21 divided by 8. We can do a decimal for this one. So 21 divided by 8 gives us 2.6 meters per second squared. Now, acceleration is a vector, so we do have to give it a direction. Now, because the final velocity was heading east, acceleration is going to be in the same direction for us. So therefore, he accelerated at 2.6 meters per second squared east. All right, there you go. Second example, a cyclist traveling initially at 15 meters per second. So list our information. Initial velocity, or the first velocity, is 15 meters per second east. brakes smoothly and stops. So final velocity when you stop is obviously 0 meters per second. And we did that in 5 seconds. What is the average acceleration? So your average acceleration is delta V over delta T, V over T, V1, or sorry, V2 minus V1. So 0 take away 15 over 5. And the whole key here, 0 take away 15, is negative 15, and you always check that with the calculator. We're going to end up with a negative acceleration. All right, so therefore, he slowed down at 3 meters per second squared. And we'll go east. Why do we end up with that negative? It's because of this right here. We are decelerating. So it makes sense that the formula produces a negative result. So if you're slowing down, your acceleration will give you a negative result. All right, final slide here. Acceleration due to gravity. Now, some of you, or hopefully all of you, know that gravity is 9.81 roughly on Earth. Okay, so acceleration on Earth is 9.81 meters per second squared. And that's approximately. Now, we give it the variable. It gets its own variable. G is assumed to be 9.81. Okay, so if you see the letter G in a formula, you know it is our gravity on Earth. So looking at two falling objects, misconceptions versus facts. All objects fall at the same rate. All right, all objects fall at the same rate. Now, you're going to say, well, I disagree with, maybe a bowling ball and a feather. I agree completely. So I have to put the stipulation, this is true in a vacuum. Okay? Under real-world circumstances, there are other forces at work here. There is your air resistance, like a parachute. That air resistance will keep you falling or accelerating at 9.81. However, it is true that all objects will fall at the same rate. So if we took our bowling ball and our feather, what a feather, nice, okay, we are all accelerating or falling at 9.81 meters per second squared. All right. The difference is in what's pulling us up. Okay. So force, and we haven't used the word force yet. That's why I'm kind of hesitant to use that word. But what's stopping us? Or what's stopping it? Okay, so a bowling ball is going to cut through, it's going to have less resistance, so it will fall faster in terms of velocity, but it still has that same acceleration. But surface area, so factors like surface area play a large factor. Now, how heavy an object is has no impact on gravity on the 9.81. It has no impact on that acceleration. In terms of force, yes, and we're going to talk about this a little bit later. So at this point, you got to trust me in terms of really surface area is the major factor that influences how fast an object will fall in terms of velocity. But this statement up here is true for all objects. All right, and we're going to do a couple of labs and demos to help kind of wrap your head around that, and we'll have some discussions to clarify. All right, So that being said, I'm going to let you do some of the homework. Any questions, let me know.